Okay, in this video, we continue our discussion on angles that are inscribed in a circle. The first thing we want to note, I'm not going to do maybe a very simple proof, but this should be an obvious fact, that congruent chords, that means two chords of the same length, intercept arcs of equal measure. So, in the two circles, I drew two chords that have the same length, hopefully. I did my best in the picture. So let's show that by maybe putting a little notch through them. Those two chords have the same length. So if that's true, if the length of xy is equal to the length of x prime y prime, as we've shown in the picture, then the arcs they intercept also have the same measure. So I will say then arc xy, the measure of arc xy is equal to the measure of arc x prime y prime. Oops. Like that. So let me draw the two arcs. I'll draw like this. The measure of that arc is the same as the measure of that arc. And that's simply because they have the same central angle. That angle, ooh, goodness. That's a bad picture. That angle is going to be the same as this angle. Okay, now let's take one look at a new theorem, and we'll do a kind of a proof sketch of it, and that'll be all we do in this video. Theorem called inscribed angle. It's going to be very similar to, or a generalization of, the lemma that we looked at in the previous video. If you take an inscribed angle of a circle, it has measure equal to blank that of its intercepted arc. Well, if you remember from the previous video, we used 1/2. I'll write it out, 1/2. You can just write 1/2 if you'd like. Okay, so here's what the proof is going to look like. 3 cases. When we prove the 3 cases, they're the only 3 possibilities. We will be done with the proof. Okay, so the first one, let's just describe the cases first before we do the proofs. Case 1 is the inscribed angle meets O. In other words, one of the sides of the angle meets the center of the circle. That's the case we did in the last video. The second case is that O, the center of the circle, is in the interior of the angle. And the third case is where O is in the exterior of the angle. So we've got the inscribed angle here, but it does not contain the center. The center is outside or exterior to that angle. Okay, well, in the first case, remember, we have a side that goes through the center of the circle. So we know that the measure of angle ABC is equal to 1/2 of the measure of arc AC. For this case, proof is complete. I will say by half arc measure maybe abbreviate it HAM lemma. That was in the previous video. So all we're saying is this angle right there is 1/2 the measure of that arc. Okay, well, we're going to use that half arc measure lemma again in the next cases. In this case, we have that the center of the circle is on the interior of the angle ABC. Okay, and maybe I shouldn't have called it ABC if I'm calling the circle C. So maybe I'll just say let O be the center of circle W. Okay, that doesn't change anything in here. All right, so now we have this, and what we're trying to look at is the measure of angle ABC. All right, so what is that equal to? The measure of angle ABC is equal to, notice these are adjacent angles, they have common vertex B. What is the measure of angle ABC? It's the measure of angle ABD plus the measure of angle DBC. Let me write that. The measure of angle ABD plus the measure of the bigger of the two angles, DBC. Okay, what's the measure of angle ABD? Notice that the measure of angle ABD, in that angle, one of the sides passes through the center of the circle. So we know what this is using the half arc measure lemma. This is 1/2 the measure of the arc AD. Plus, what is the measure of angle DBC? That's an inscribed angle. And one of the sides passes through the center of the circle. So we can use the half arc measure lemma from the previous video. That's going to be 1/2 the measure of arc DC. And just using arcs that are adjacent to each other where they share one point, you can add the arc AD plus the arc DC, and what do we get? We would get arc AC. So if we take 1/2 of AD and 1/2 of DC, we'll get 1/2 the measure of arc AC. That's exactly what we're trying to prove. Excuse me. Last case, we'll do pretty much something similar. In this case, the center of the circle is exterior to the angle. So, what is the measure of angle ABC? Well, it turns out, by just summing adjacent angles, the measure of angle CB, let's see, that would be D. The measure of angle CBD is equal to the sum of the two adjacent angles here. It's equal to the measure of CBA plus the measure of ABD. So if I simplify that, the measure of angle ABC is equal to the measure of angle DBC, the big one, minus the measure of angle DBA. Well, what is the measure of angle DBC? It's an inscribed angle that contains the center of the circle. So the measure of angle DBC, the big one, big angle, is 1/2 the measure of arc CD. And minus the measure of another central angle that uses the center of the circle, DBA. DBA, this small angle, is going to be 1/2 of arc AD, minus 1/2 of the arc, the measure of arc AD. So we take the big arc, CD, well, half of it, but just note that the arc CD minus the arc AD gives us the arc CA, or AC. So that's going to be 1/2 of the measure of arc AC. And we're done. We've proven all of the cases. So once again, an inscribed angle of a circle has measure equal to half of its intercepted